Hello class. So sorry I wasn't there today. Hopefully you were able to work on the force problems. I know some of the later ones are kind of hard. How do these forces work? Hopefully you're able to try them. We of course are not going to be done with this subject for a while, but I do want to talk about something we've actually been talking a lot about. I just didn't give you the names for them. And this will be vectors and scalars. So in this video we're going to talk about the differences between them, how they relate to forces, and then using mostly the word vector, we're going to talk about the intro to force components. Alright, so first the definition. Vector, I've used this in class, but we never properly defined it, so please write this definition in your notebook. Vectors are something that has a magnitude let's rewrite that. Magnitude just is another way to say size, like when they talk about the magnitude of an earthquake, the size of an earthquake. The important part is that it also has and a direction. So remember we said a lot of these things, well, okay, they have an amount size, right? Like say the velocity is 4, but we also care about the direction of it, such as it's 4, in the up direction. A scalar only has a magnitude or a size. We don't really care about the direction, or it doesn't even have one. So, for example, this is the main difference between velocity. Right? When we talk about velocity, we need it to be a direction, so we could say 3 meters per second towards the right. But if we're talking about a scalar would say be your speed, like in your car. And our car does not tell us which direction we're going. You would say be going 3 miles per hour. As far as direction, we don't know. Scalars don't have a direction. Another way to illustrate this would be, I'm erasing my examples. These are all examples of. Another example of this would be, for example, when we talk about forces and weight versus mass. Alright, mass does not have a direction. It's how much of you. So, for example, let's say you're 76 kilograms. There is no direction on this. However, your weight, although they are similar and are often compared and treated the same on Earth, because they could be the same on Earth, your weight is not the same as your mass. This is your mass times gravity. Remember, gravity does have a direction. Gravity's direction is down. Whenever you multiply a vector and a scalar, it now has a direction. So your weight, for example, could be something on the order of, say, 760, that'd be negative newtons. Alright, so because I remember this, your mass was 760 kilograms, your acceleration for that was gravity, which is negative 10 meters per second squared. You multiply them, you now have a direction. So the direction for this, remember, it's negative, and we are talking about gravity, so this would be, down. So the important part to remember is that vectors and scalars are really similar. They both have a magnitude and a size, but a vector must have a direction associated with it. As to how it relates to your forces, force is a vector, therefore every time you have a force, you must have a direction. You cannot just say, we have this box, there's gravity on it. Every time we do a force body diagram, this is why I have you draw arrows in the exact direction. As far as how long they make them, right, the direction is the way the arrow is pointing. The magnitude of our vector is how long our arrow is. So remember when I said you want for, say, gravity and our normal force? If we have a box that's just sitting on a table, its free body diagram would have a force of gravity that was equal in magnitude, but in the opposite direction of its normal force. So the fact that both magnitude and direction do matter in our free body diagram, so always check on those. Alright, so vector components. Alright, we've already talked about how we can have forces in both the x direction. Here's my x direction. And we can have forces in our y direction. However, as nice as this kind of looks in a coordinate plane, that's not how the world works. Hopefully you know things can go in more than just side to side and up and down. We can have forces, say, in any number of different directions. However, if we have these in all these different directions, it is not necessarily, let me actually redo that, each one a different color. It's not terribly clear if these are all these different forces, where exactly will our object be going if it has all these different forces on it? It's not very clear. So to make it clear, every time we have a force, we break it into its components. By components, each one of these has both some magnitude and some direction in both the x and the y. So we have to try to figure out how to break it down into each different sector. So the way we do that is say, okay, well, this, for example, this green line, it's in the x direction, it is going, left just this far in the x direction, and it's going up in the y direction in this direction. So we break it down and we can kind of actually get rid of the original line and say, okay, these two together, these count for that line. Same thing, for example, the red line, we bring it up here. Notice, look, these are almost the same magnitude going in the positive y direction, so these are actually going to add up. And that takes care of the y direction, and then in the x direction, again, look, it's almost the same. Do the same with our orange. It's almost the same in the orange direction, but then there's some subtracting we'll have to do here. So if you erase all of these lines, now it's a little easier to solve mathematically as far as now that we've broken it down to both x and y. So this would be what your diagram would look like in just the x and the y direction, and you could find the numbers for these, right? You have the force going up minus your force going down, then you subtract your force going to the right minus your force going to the left, and you would get something in the range of, see, this is going to cancel this out a little, this is going to cancel this out a little, but really it looks like it's going to be going both this direction to the right and up, so we're probably going to get some line in this direction. We'll talk more mathematically. I just want a brief introduction to it. So to clear these drawings, when we talk about vector components, let's just do one really quick. We will be using geometry. So hold on, it's only one thing you guys are going to have to really be good at. Hopefully this phrase seems familiar to you. No, it's not some weird kind of chant. So SOHCAHTOA stands for sine is equal to the opposite over the hypotenuse. This is cosine theta is equal to the adjacent, over the hypotenuse. And TOA stands for tangent of theta is equal to the opposite over adjacent. So what this means is that for any triangle, because when you break your vector into components, hopefully you could think, oh hey, look, every time you do that you make a right angle. So if you have this angle here, this goes in for theta, you can, if you know one of these, if you know two of these three things, whether you know either the sides or the hypotenuse or the angle, as long as you know two of these things, you can solve for. We'll practice it, but this is how we're going to break our vector into both its x and y components only, so you can solve these. Hopefully this is informational and you took notes. We will continue talking about this, but we're going to go back to working on our projects tomorrow. Alright, see you tomorrow.